Share my screen. Can you see my screen? Yes, now please.
Yes, sir.
Okay, good. Okay, so let's get back to what we were doing. So we were talking about distance vector routing. We discussed this. We worked out a very small example. We will continue from there. So just to recapitulate, so it's a distributed protocol, which means every node will do something. Okay, and that something is that every node keeps a routing table. You have seen the entries of the routing table. So for every reachable destination, that means nodes that this node can reach through some path, it will keep what is the next hop. So the next node it should forward that to, and the cost of that thing. The cost can be many different things, as we have seen. We'll discuss it later. Okay, but some notion of cost to that route. Okay, which will be nothing but some of the link cost. But link cost can be, as I said, number of links, some delay, throughput, whatever, bandwidth, etc., etc. So the way distance vector works, just to recapitulate, is that every node periodically sends its routing table to its neighbor. Okay, all the entries it has, just to its neighbors. Okay, and then when I receive a routing table from one of my neighbors, I look up for two things. There are two possibilities. So I look at every entry that comes into me. So for the routing table that is sent by my neighbor, I look at every entry of that routing table. Now there are two possibilities. Either the destination for which that entry is, either it is in my table already or it is not. If it is not, that's a simple case. It's basically telling me that that node knows a route to some destination that I still don't know of. So I will just add that route at the node as my next stop. Okay. On the other hand, if I have a route already to that destination, okay, I will see, is it okay to follow that route that I have, or is the route that is coming to me is a better route? So this was the simple case. So this is me. Okay, I already know of a route through somebody else, and this is the incoming table coming in. Okay, and so I will see, look at the cost of that I have in my table and the cost that it is advertising plus this link cost. And if this comes out to be smaller, I will change my route from here to here, which basically means I will change my next stop from here to here, and I will update the cost. Okay, so this happens if the new route found is to be less costly than the route that I have. But then there is this one case, if I see that, so this is what we say, always trust the next hop. Okay. But in the other case, even if the route cost is not less, if I see the route is coming from this, and this route that I have is actually through this, the already existing route that I have, then I will update it anyway, because I have earlier updated this with this as the next stop with the information that it has about the rest of the network. Okay. Now, if some link out here had a cost of 1 now, and now for some reason this cost has changed to 3, okay, only this node can know eventually. So my way of knowing this cost has increased only through it. So if it has told me earlier this was something based on 1 and I've trusted it, now it is telling me the cost has increased because it has come to know. I don't need to know where it has come to know and something. I will always trust it. So I will update if the existing route is more costly than the incoming route, or if the incoming route is coming from the same next stop as the one that I have in the existing route. So this is something that we did in the last class. Worked out an example. Let's go quickly through maybe another. I think we have worked this out. Any confusion of the basic example that we have worked on? Should I work out another example? Again, is it yes or no? I have no problem either way. Did you understand the last example? Did you take a look at it after the class? अरे कोई yes no कुछ बोलो यार.
Yes, sir.
Okay, so you understand it. Do I have to repeat it or not? Okay, let's do some protocols. Okay, silence will be taken as in my favor that I don't have to repeat it. So I'm asking you again. Do you want me to work out the example again? I'll give you another 15-20 second break. If I hear nothing, I will assume that you understood it.
Yes, sir.
Yes, sir means workout.
Another example, sir.
Okay. Okay, good. Okay. Actually, the line example is kind of the best. Okay, but okay, fine. Let's at least the line example has only one path to show basic thing. So let's do something like this. Okay. And let's put some costs. So let's say I put a higher cost here. Okay, and then 2, 3, 4. Okay, and let's give this thing some name. So let's call A, B, C, D, E, F. Okay, so there are two paths. We'll see. So one thing that you have to kind of visualize, because now the algorithm that every node is running is distributed. Okay, so you have to kind of think of this something that is very crucial when we teach you distributed algorithms in distributed systems. You think that you are standing outside the network and you can look at the entire network. That's mythical. You will never be able to. No, you cannot look at the entire network always. Okay? But think about it as if you are an observer. But every node is doing something, sending messages, taking some action based on that, and so on. But then you kind of abstract yourself out of the network as an observer, and you're observing what is happening. You say, oh, this message is going to that node. That message is received by that node. This node has updated its table. Okay? And then eventually, if you look at the entire network, the right thing should happen. That means everybody should have the routing table properly and so on. Okay? So that's the kind of way of looking at it. When you reason about the thing, you kind of look at the entire thing. Even when you design the algorithm, you are kind of looking at what will each node know, what will each node not. So this node will not know even that the topology is like this. This node only knows its neighbors, that there's two neighbors. It does not know the network beyond it at all. Okay. So that's the first thing to remember. The second thing to remember is that even we said periodically, say every 30 seconds. That's a typical thing in internet routing. Where one of the protocols that follows distance vector routing, we'll talk about it later on. Okay. So it sends the routing tables every 30 seconds. Okay. But then the other thing is remember is that this is kind of a large, some machines spread over, let's say CS department, etc., etc. Their clocks may not be synchronized. So do not assume when you reason about these algorithms, okay, do not assume that everybody, even who will say every 30 seconds, everyone will do. This is doing it according to its clock's 30 seconds. This is doing it according to this clock's 30 seconds. This is doing according to this clock's 30 seconds. So clocks may not be exactly synchronized. It's not that it will happen exactly at the same time. There will be slight delays here and there. And then getting the message over here, okay, will not be exactly the same. So even if this and this sends the message to this exactly at the same time, just suppose, even that is not guaranteed, this may receive this message earlier than this one, or vice versa. If it receives both of them, in what order it processes them is arbitrary. So don't have this idea when I said everything is kind of synchronously getting updated together. All of them are coming, this looking at all of them and changing it, taking the best one or something. It just tests, node just waits, gets one of them, and just updates. And when we do IP, I'll point this out. This is nothing but again another protocol running over sockets, sending messages to each other, just like you have done in your lab or doing in your lab. Okay. Okay. With this, let's see. So what I will do is, why I'm saying all these things, I will let this propagate first. Okay, I will let this path, this 30, 20, 10 path propagate first, and then kind of update it when the 2, 3, 4 comes. Okay, so initially your routing tables are empty. So just take a look at what happens after the first thing. So D will have an entry for A. Initially, it has no entries. Okay, so first step, let's say one step, everybody, this step forwards to this forwards to this forwards to this, and these things forward also. Okay, up to this, let me do this. Okay, just give me a second. That example doesn't become too big, but I still show you what I want to say. Okay, so fine. Let's just suppose that C to A, this message is the one that is getting lost again and again. Okay. So first step, after the first 30 seconds, what will happen? Everybody will get their neighbors information. So I will just show, I will not draw the routing table of F. Okay, the same thing will happen. Let me draw it for D. So D will basically know that F, okay, is directly connected to it with a link of 30. B is directly connected to it with a link of cost of 20. Okay. E will know F is directly connected to it with a link of 4, cost of 4. C is directly connected to E with a cost of 3. Okay. Because F is just sending just a message, pure hello message basically. C then knows basically after the first step that it has E directly connected with 3, A directly connected with 2. And this message is getting lost. Okay, the C to A message. Okay, so what does B know? B knows D directly connected with 20 and then A directly connected with 10. And A only knows B directly connected with 10. Okay, this C to A, this update has got lost. Okay, I'm deliberately losing it because otherwise these routes will never change basically. Okay, one of these. I want to show that a route changes in A case. All right. Okay. Next step, what will happen? Next step, basically, this thing will propagate. So now B will receive, okay, the routing table of D. Now B receives something for F, something for itself. Itself does not matter. Okay. So this is a new route it has learned. F, this is saying 30, this is saying 20. So it will add a 50 out there. It says basically I have a route with these 50. Okay. And then similarly, it has sent the D and A to this. A it does not send the next of base. So A is not this. So we'll add a D, 20 plus 10, 30. The F has not come here yet. At this level, F has only come here. It will depend again on this timing, whether D to F comes earlier before B sends to A. In which case, the table has already been updated with F. In which case, B's update will also contain the F. But I'm assuming that B has sent it earlier and then received the D to B. All right. Similar things will happen here. So now F will advertise. Okay, let's do that F thing. F will have a D 30. Okay, and then E 4. So F will advertise this, and then I will get a D 30 plus 4 34. Okay, E will not be changing because E is itself. Okay. Similarly, E will advertise and C will get an F. Sorry. Wait. There is something wrong. I made a mistake. This was odd leak, so this will not be F. This will be FD, right? Because B is getting a route to F through D. Okay. Similarly, this will be B30. Okay. Because the routing update came from B. B is saying they have a cost to 20. So A does not know of the path. So 20 plus 10, 30, new route, but the next stop is B. Okay. So similarly, this will be DF34. Okay. And then this will be FE7. Okay. Okay. So now let's have one more hop. Okay. So this now knows if I'm not updating the other ones, B This will come as 50. So this will come as 60. Okay, some more tables will change out. But after B broadcasts this table once more to its neighbor, this will change here also. I'm not just showing these changes. Okay, this will update this. Now let's see in the next 30 seconds when C broadcasts. C was broadcasting. It's not that C was not sending to A. Some of this was getting lost. Just suppose. I just wanted to delay things basically. Okay, or lost, or the original one was delayed or whatever. Now C sends another update and it comes here. Okay. So what does DC? Sorry, AC. So A's routing table now has, let's draw this a little neatly, DB30, BB10, FB60. Okay. And it has got basically EE3, AC2, FE7. So first thing, it looks at EE3. It sees the table does not exist, doesn't exist anything. So it adds this E. It has gone from C. So next stop is C. 3 plus 2, 5. Okay. Then it sees AC. It itself is A. Nothing to update basically. Okay. A to A route is already. Then it sees the F. Okay. It sees it already as an entry to F through another next stop, not the same next stop. Okay. So now it sees, looks at the thing, it says, oh, this is 7 plus 2. That means if I go through this, my total cost will be 9. The cost that I have is 60. 9 is less than 60. So I'll take this out and update F to C9. So it will start using this route path for routing to F rather than this path. Is it clear so far?
Yes, sir.
Okay. So that's an example of a route changing because the cost goes down. Okay. So now it has this route. Now what happens if this 3 cost now goes up to 10 for some reason? Let's say you had a delay and something happened. There was too much traffic coming in. The delay has increased. So for some time, so now see, that is the observer thing. You think that you are standing with a clock in your hand, kind of a mythical global clock. Okay. Then you immediately see this 10. But A has not seen it. A can only see when C detects it. There are some local mechanism for detecting that. Okay. And then C advertises in the next 30 seconds later, C advertises this to A. Okay. So when C advertises this to A again, okay, then C will advertise this cost as 4 plus 10, 16, sorry, 14. So now I will get a route coming in among other things saying, I have a path to F through E, okay, with cost of 14, and I have a path through E, okay, with a cost of 10. So this is what C will send to it. All right. Now, both of these entries are there in A's routing table when A receives it after that 30 seconds. So it will see, I have a path through C with 5. Now C is telling me it has a path through E through 10. 5 is already less than 10. But because it is coming from C and C is the next stop, I'll blindly trust C and increase this. Same for F, I'll blindly trust C and F. Because C has told me something has happened beyond in the network, which has increased the cost. So my earlier information was also through C. I will always trust C. Now C is telling me something more, I will just do that. Is that clear? Those two cases when you update the rules?
Yes, sir.
Okay. Okay. Let's move on. What's the problem with this thing? Okay. So I have a picture, but let me draw it anyway. So think of a simple case. You have A, B, C. Okay. And you had a cost of whatever. I don't know, 1, 2. Okay. So C's routing table, if you look at it, it basically says I can reach B through B with a cost of 2, and I can reach A through B with a cost of 3. B's routing table said I can reach A to A with a cost of 1, C with a cost of 1, and A is something. A is not important for us. Okay. So this was a stable state. Packets are being forwarded. Everything is fine. Now suppose this link goes down. Okay. Now what will happen? B will detect the link going down. That's not part of your routing protocol. As I said in the last class, there has to be some lower way. Basically, we call it a hello protocol or something. You periodically think that thing something, or you expect some lower level packets to come. Some protocol has to run to detect that the link is up or down. Okay. So link goes down. Okay. B detects it. Just suppose. Again, the timing is very, very important. So B, what it does, sorry, this was CC2. Okay. B changes this to say A is no longer reachable. Okay. And to say no longer reachable, it puts a value of infinity. We'll see what infinity is. Okay. Just now, right now, let it be a symbol infinity. All right. Now it's the critical thing. Now, periodically, B and C will exchange their routing tables. So, if B sends its table to C before C sends, what will happen? C will get an entry A, this infinity. It's coming from B, its next hop in the already existing route. It will always trust the next hop. It will update this to infinity. So this information, what was the infinity signifying? Infinity was signifying that B no longer has a path to A. Okay. And that information will propagate. So everything would be fine. A will say infinity. So no route. Basically, the 4 packets will start getting dropped destined for it because B does not know or C does not know any packet link to A, any route to A. Okay. So all okay. But what if C's update reaches B first? What has come? Now, in the update, we basically just send this. So this has come. Okay. Now, look at the update rule for B that we have seen. It will look at an entry for A. Yes, it exists. It'll see what is the next stop. Is C the next stop for this entry? No. Okay. So it was actually, if I don't change it, it was actually A. So the next stop for my route is not the same. So no question of trusting the next stop or anything. Okay. So that part does not apply. It already has a rule. Okay. And 3 plus 2 is less than infinity. Infinity is high infinity. So what will happen now is that B's routing table will change to A, C, 3 plus 2, 5. And this now has A, B, 3. The CCC is unimportant, so I'm not writing this. Okay. Now if you're unlucky, now B will send this. When B sends this, for C, it's getting a route to A, already exists. B is the next stop. Always trust the next stop. Still update to 3 plus 5 plus 2, 7. Then this will send it. The same case will happen. This will get updated to 9. So basically what you have got is a routing loop. Okay. So this update will propagate and push up the value here. This update will propagate and push up the value here. Are you with me?
Yes, sir.
Everyone, again, I will wait for a little while to sink in. So this is what is called a counting to infinity problem. Is counting up to infinity. Now, infinity is infinity in the mathematical sense. It should never stop, but we'll see how to stop this. Yeah, sometimes, but remember, each of those convergences are happening So rather each of those updates are happening after the table gets propagated. And tables are only propagated periodically. So even if you had, rather than 1 and 2, only 1 and 1, so at every step it goes up by 1 only, okay, in the worst case, then each of those one update here is happening, let's say after 30 seconds. So for this to go up by 1 and this to go up by 1, you have already taken 1 minute. Then it will go up by 1 again, another 1 minute. And remember, while this is happening, the tables that entry for A is all wrong. Nobody has a route to A. So the packets that are coming in to be forwarded, they are just going in a loop out here. This is for sending it to this is sending it to this. This is not reaching anywhere here. So this is a problem. Counting to infinity is a problem, standard problem, well-known problem with distance vector routing protocols. And if you just note one thing, it did not even have to break. Excuse me. It did not even have to break. Break is basically when I set it to infinity. If that cost has increased to something very large, okay, even then you can actually have a loop out there. Basically. If C's update, so you get this 100 here, but then C's update can come and kind of erase this 100. Are you with me? Yes, no? This last thing, did you get it or not? See, what I'm saying is that this cutting this link is basically, I set a value of infinity, but say instead of this link going down, suppose this cost had gone up to 1000. Then this value would have come to 1000. Okay, but this 1000, if it propagates to C, C will say trust the next stop, let me do 1002. But then because this was 1000, okay, then this, if C's update comes to B before B's update goes to C, then the same problem can happen, because B will think that there is a path to A with cost lower than 1000 through C. If I don't change anything, B does not know that that path goes through B itself. So there is no point taking that path. But B will wrongly think there is a lower cost path to 3. So B will again update this to 1000. Sorry, just to 2 plus 2, that is 3. 2 plus 2, 4. Okay. And once that is done, this 1000 is lost. Okay. Are you with me or not? Yes or no? Okay. Yeah. So to solve this, what is the problem here? The problem was that this infinity was getting wiped out. There's another thing to note out here. See, this link is gone means, and it has B has detected the link is gone means this route does not exist. But if it does not exist, you cannot just remove the A from the entry of B. You have to tell others that it does not exist. Because everybody else has a path through this, then there may be another node D with a path through to A through C, there may be other nodes out of the node. So all of them have a path through this, but this has broken. So B cannot just simply remove this route. They remove this route, there is nothing in my rule. Note that when a routing table comes in, I just look for two things. Does the route exist in my table? If not, I add it. Or I say if it exists, modify it if necessary. There is nothing to say if that route does not have it, and I have it, I will delete from my. Okay. So if B has simply deleted this, then this A route would have stayed in all of them, and any packet generated for A would have come all the way out here and got dropped at B. So that's why you have to set it to infinity. You don't delete it. When I do routing information protocol after doing IP, I'll tell you what happens. Eventually, how do you clean up? We'll talk about that. But you have to give sufficient time for the infinity to propagate if you're lucky, so that everybody will know it's unreachable. Infinity is a special value, it's a no, not reachable. Okay. Okay. So the problem was that the infinity was getting wiped out. If the infinity propagated to C before C's 3 propagated back to B, okay, I would have been fine. infinity would have wiped out the 3. It's just that the 3 got wiped through, infinity wiped out. Now there is no infinity, so nobody's table will change. With me? Yes, no?
Yes, sir.
Okay. So, first solution. Can you think of a solution? Simple thing. So let me give you a hint. Should A have sent this route back to B? Is there any benefit of A telling B that I have a route through you? Not say, sorry, my mistake. C telling B, my mistake, not A telling, C telling B that I have a route through A through B on. Is there any benefit? What will B do with it? Right? We cannot do anything with it. There's no extra information to do this. So we do many different things to solve this. Okay. First is called a triggered update. It's a simple thing. Remember, it was a race. It was all basically timing issues. When you do OS, you will have, when you start doing process synchronization, you will see again this. Whenever there are things happening in parallel, be in the same machine, be over the network or something, these timing differences can make a lot of problems. So in this case, it was, note that suppose this link changed, okay? So there was the infinity already here and there was the 3 already here. So this 3 would have propagated to this after some time. So if I can make the infinity propagate faster than this 3, my problem is solved. So triggered update does this. When it says when a link failure is detected, okay, trigger the update immediately. Propagate the information immediately without waiting for the next update. So if you are lucky, then this were each sending you update in 30 seconds. So rather than, so suppose this happened 15 seconds into the 30 seconds, you would have sent the infinity after 15 seconds. And maybe this is sent after 12 seconds. But then you are sending the infinity immediately so that it wipes out the 3 out there. The infinity propagates. You just got to make the infinity propagate fast. The second one says split horizon, which says what I just said just before this. It says if you have received something from this node, okay, so this is my C, this is my B. If C has known about a path for B is next stop, don't tell B that path back because B cannot do anything with it. There's no extra information with it. Okay, so do not advertise a route to a node from which the route is learned in the first place, which is the next stop basically. So C has learned about the route to A from B. So C should not, when C sends his routing table to B, it drops all the routes which has B as the next stop. So that 3 will not go in there at all. Okay. So in our case, what will happen? In the earlier case, you had B, C, B had A infinity, C had A, B, 3. Okay. And this A thing is broken now. So C will never send. When C sends the entry, C has other entries, etc., etc. C will send, when it sends the update, all those entries, but this A, B, 3 will not be sent. Because B is the next stop, I'm sending the entry to B only. There's nothing that B can do with it. There's no extra information for B in it. This can never be less than what the entry that B has for A, because this is going to be positive weight, so this is going to be this adding up to this. Are you with me? Yes, no?
Yes, sir.
Okay. But I would like you to verify. Okay. So these are the things I want you to work out yourself. You work out an example. I can always draw examples, and I will do that if you at the beginning of tomorrow's class if you find a problem. Okay. But I want you to work out. Take a simple example. Okay. Just extend this to this and make this link fail. And then you apply split horizon. So obviously triggered update does not solve it fully, because if you're unlucky, this infinity change could have happened, as I said, because these three clocks are not exactly synchronized, so everybody will not send exactly at the same time and so on. This infinity change could have happened just at 29.5 8 seconds. And by that time, this has already sent it because the clocks are not synchronized and this. So it sets the infinity before it can send it out. This comes in, it wipes it out. Okay. So triggered update does not solve it for you. Split horizon will break all 2-node loops. What we have shown you earlier is a 2-node loop that will always be broken by split horizon. But try to prove that a 3-node loop is not broken. Okay. So let me give you a hint. Just put a cost of 10. I can do it with a cost of 1 also with a slightly larger loop. And let's say these arrows show who the next stops. So obviously this has a edge to this, sorry, route to this through this with cost 1. This has to cost this. Okay. Problem is, it's obvious, when this becomes infinity, after this detects, this will not send to this because I have split horizon. This will not send to this split horizon. But this does not know that this link is something. This will still send this 2 to this. So when this advertises the route, its routing table to this, okay, this will still say this is A, that I have a route through A. Let's do the same thing, B, C. Okay, let's call this D with the next stop C with cost 2. So 2 plus 1, let's say 3. And then when it comes to this, if you look at this, its own thing is infinity. Okay. So split horizon will not stop it because B is not the next stop of D to the route to A. So D will send it. And then this will find a lower cost route 3 plus 10, 13. 13 is lower than infinity. It will update the route. And once that happens, it will send this. This will trust the next stop. It will do 13 plus 1, 14. This will do 14 plus 1, 15. This will do 15 plus 10, 25. And this will go on. Are you with me? Yes, no? Okay, good. Again, see, it's on online class. If you have a problem, please let me know. Okay. You can stop me later on also. Poisson reverse is just the other way. So split horizon says, do not send anything to the next stop. Poisson reverse send it, but send it with infinity, which is basically saying don't route through. So this is just 2 ways of saying don't route to me. Split horizon said, don't route through me because I'm not telling you that I have a route. Okay, I'm not sending you anything. Whereas Poisson reverse says, don't route through me because I'm telling you it's infinity, which is telling you explicitly that there is no route. So one is kind of keeping silent. I have not told you anything, so there is no route. One is explicitly saying, I don't have a route, I don't have a route, I don't have a route. Okay. So the same thing basically, Y is the next stop for Z. If you have a Z, Y, okay, and X. So Y is Z is reaching X through Y. Then Z advertises when it sends its routing table, all the other routes that Z can reach, Y can reach, etc. is sending. Okay. Along with that, it will send you a X, Y, infinity. Okay. So note something that the purpose of split horizon and Poisson reverse are kind of the same. In split horizon, Z will not send anything to Y. So Y will not receive this route. So Y will not be able to route through Z to go through X, even if it becomes infinity. Okay. Whereas in this case, okay, Z is going to send this thing to the next stop, but it is advertised as infinity, which means this can never, infinity can never be less than infinity. Okay. So it's going to be, Y will never try to route through Z to go to X. That's something that Y has advertised. So the natural question comes that if both of them are the same, serves the same purpose, split horizon seems better, right? Because this sends an extra message. rather not extra passage, one more entry, additional entry, some more, so message size increases a little bit. And this it will do for other entries also, basically to other next steps. Note that in normal case, when Z advertised to something else, okay, and if this was 1, this was 1, this was 1, okay, then Z will, let's call this node P, okay. So Z sends to P, it will send X, Y, 2, the correct route. It's only to Y that it will send X, Y, infinity, just to the next in the normal case. Even when everything is fine, Y has told him properly that there's a route with distance 1 to X and so on. Is it clear? Yes, no, please.
Yes, sir.
Okay. Like to hear an yes from somebody else. Is it clear to the rest of the class? Somebody else?
Yes, sir.
Okay. But you can show that none of these combinations can solve the counting to infinity problem fully. It just reduces the chance. Then another thing called hold down and all that I'm not going through. Okay. So I've already shown you, like, split horizon, I've already shown you that why it cannot do this. Poisson reverse, the same thing can happen. Okay. It's okay if you send the infinity, but then, when you this going back the thing, that 3 coming back to you, can same thing happen through these 3 node loops. So either split horizon or Poisson reverse will always break 2 node loops. But again, please do this yourself. I've told you kind of the idea with the 3 node loop. These are classic exam questions. Okay, also simple exam questions just to understand whether you understood the concept. Okay, so if that is so, if triggered updates, split horizon, none of them are, we can employ them, reduce the chance, but there's always a chance that this loop will continue. The chance that will continue will be less, but once the infinity is wiped out, you're gone. Then it will continue. Okay? The infinity has to stay there. The infinity is the indicator that there is no route to that. It's kind of telling people that there is no route to that by telling that the route cost is infinity. Okay. So once the infinity is gone, because you have bad luck, it will just keep on increasing. So what do? Basically, you put a bound on infinity, as strange as that may sound. Okay. So if you have a network with n nodes, what do you think that bound can be? Okay, it's not a good question to ask because in general it's tough to answer. So you have to put a bound on infinity somehow. Okay, so here's an example. Okay, you put your cost equal to number of links. Okay, then what is your infinity can be? Number of nodes equal to n. Then infinity will be greater than equal to, what's the maximum possible length of a path? N minus 1, right? So it depends. Okay, so indirectly what we say is that, okay, fine, for example, this will shortly, we have done most of it, okay, but we'll just refer back to it. This is internet protocol called RIP, routing information protocol. Okay, RIP says that cost equal to number of hops, you can only use that as the cost, nothing else. Okay, infinity equal to 16, which implies maximum 16 nodes. So you want to use RIP. So this kind of the kind of the constraints that distance vector routing imposes on the network. So RIP is a distance vector routing protocol. It will say the only type of cost that you can use is the number of hops, and the value is set to 16, which means it's only good for very small networks with around 15 nodes, 16 nodes. So that the maximum length of the path is n-1. So if a router sees this cost going up to 16, that means there's infinity. That means there is a bill. In which case it will just break everything, just remove the thing, set it back to infinity, and then won't use that route to forward the packets anyways, basically. Because remember, this routing thing, when it's going to 2, 3, 4, 5, 6, 7, all the way to 16, if the packets are coming, this is like a valid route to the router. So route is sending, but what is happening is the packets are just circulating in that way. It is not reaching the actual destination, because the actual destination, A in our case, does not even have a path from that node. Okay. So distance vector is used for small networks. Okay. And you have less flexibility as to the number of hops and so on, and as to the definition of cost that you can use. Okay. But then, as I mentioned, there is something called path vector. Okay. So path vector is a variation of distance vector, which is, it works in the same principle as distance vector, but then, well, just it's not in the exam, so you don't have to remember it or anything. Okay. But basically, rather than just sending the cost, the next hop, okay, it will send you the entire path. So where in the earlier case, suppose you have something like this, A, B, C, D, okay, and when C sends to D, so when B sends to C, B will send, I have a destination is A, okay, the path is A, then B, cost is, let's say these are 1, 1, 1, cost is 1. When C sends to D, let's say destination is A, path is A, B, C, cost is 2. Okay, same thing will happen when D sends further down and so on. So the entire path is sent rather than just the next stop. The next stop is actually, if you just think for a second, there's more implementation. Next stop is actually not sent here basically for this node, because it knows this is the next stop is. You send the destination and the cost, because D does not need to know who sees next stop is basically. I'll come back to this point beginning of next class. But path vector is a variation of this. Okay. Now, since you are sending the entire path, loops become very easy to detect. Because if you get like A, B, C, and then B tries to add B, we can always see that B has already happened before. So distance vector, in summary of today's class, distance vector has this problem of routing loops, counting to infinity problem. There are ways like triggered updates, split horizon, Poisson reverse, by which we can reduce the chance of that happening. Okay, but not completely eliminate it. So if it happens to stop it, we set a bound for infinity, and we set these two restrictions that the cost that you can use is only number of hops, and the bound is basically something on the thing. Now you can use some other cost. Distance vector per se does not restrict that, but then you have to have some bound on the cost. You have to set that infinity, say what the infinity value is to specify. This cost equal to number of 16 was just an example of one protocol that uses distance vector routing. Okay. But then there is a variation of distance vector routing that is used in the internet. Okay, very, very important protocol called BGP. Okay. So this is used by something called BGP. We'll see if we have time to do this at the end of the course. Okay. Which uses basically is same as periodical exchange of tables and so on. Only thing, rather than just sending the destination and the cost, next stop being the node that is sending it. Okay. It sends you basically the complete path from that node to that destination. So and everybody adds on to that as they forward that thing in their routing table. So then if that happens, the routing loops become trivial to find out. identify. Okay, so we'll stop here. Went a little slow, but that's okay. It was important to understand this problem. So we'll come back tomorrow, finish routing, and start off with IP. And there will be next week is the exam week. So 22nd, that is next Tuesday, you will have a proper test on pen and paper and so on. It will be around 1 to 1.5 hours, and I'll announce all the details at the end of day today or so. Okay, you will get a mail from me. All right. So if you have any questions, you can ask. If not, class is over. You can.